Dear students, in this video, I am going to discuss numerical problems which were appeared in the year July 2016 paper. So let's have a look on the very first problem. That is, charges 2 microcoulomb, 4 microcoulomb and 6 microcoulomb are placed at the three corners A, B and C respectively of a square ABCD of side x meter. Find what charge must be placed at the fourth corner so that the total potential at the center of the square is 0. Here the square we have a square ABCD. Let me consider the square ABCD here, and we are placing the charges Q1, Q2, Q3 at ABC respectively, and we need to find out the value of Q4 so that the total potential at the center of the square must be equal to 0. So that means how much charge must be placed at the point D to make the total potential at the center of the square is 0. So for this, let us consider first the given data, that is Q1, Q2, Q3, which are placed at ABC as they are given here. That is Q1 equals to 2 microcoulomb, Q2 equals to 4 microcoulomb, and Q3 is equals to 6 microcoulomb. And the side x meter we have, and we need to find out Q4 so that the electric potential at O should be equals to 0. This is the condition. For this, we know that the electric potential, let us see, electric potential is equals to 1 by 4 pi epsilon naught Q divided by R. To measure the electric potential at a point, we need the magnitude of the charge as well as the distance of point of concentration from the charge. So here the distance of this O from A, B, C, D should be considered. So that means we need to find out AO, BO, CO and DO. For this, let me consider the triangle ADC, and by applying the Pythagoras theorem, you can get AC square equals to AD square plus DC square. Thereby we can get the value of AC now. So AC is equals to, so AD square is nothing but x square, because we have a value AD equals to x, DC equals to x, so therefore x square and x square, and here we have square root. So therefore it will become 2x square. So therefore AC is equals to x root 2. But we need to have AO, BO, CO and DO. We know that AO is equals to BO is equals to CO is equals to DO, and this is equals to half of the AC. So therefore that is x root 2 divided by 2. This can be written as x divided by root 2. This is the value of AO, BO, CO and DO. Now by applying the superposition principle of the electric potential, we can have the total potential at the point O. So by using the superposition principle of electric potential, we could write the electric potential or total electric potential at O is equals to 1 by 4 pi epsilon naught, the Q1 which is placed at the A divided by distance of O from A is AO, plus, let me take 1 by 4 pi epsilon naught outside, then Q2 divided by BO plus Q3 divided by CO plus Q4 divided by DO. Now substitute the given data here, then what would happen? Let us see. The V naught is equals to, we know that the electric potential should be equals to 0. So therefore V naught should be taken as 0, and 1 by 4 pi epsilon naught value is 9 into 10 raised to 9 into 10 raised to 9. And here we know that the Q1 equals to 2 microcoulomb, that is 2 micro 10 to the power minus 6 divided by x by root 2, because we know that here we have seen the AO, BO, CO, DO equals to x by root 2. So wherever we have AO, BO, CO and DO, there we can substitute x by root 2 and Q2, Q3, so that we can find out Q4. Now let me substitute Q2. Q2 equals to 4 into 10 raised to minus 6 divided by x by root 2 plus Q3 equals to 6 into 10 raised to minus 6 divided by x by root 2 plus Q4 divided by x divided by root 2. So now you know that if this is equals to 0, then we can write directly that 0 equals to 9 into 10 raised to 9 divided by, let me take x by root 2 outside, x divided by root 2, thereby we can get 2 into 10 raised to minus 6 plus 4 into 10 raised to minus 6 plus 6 into 10 raised to minus 6 plus Q4. So now this will become now x by root 2, if it comes to the LHS it will become 0, 9 into 10 to the power of 9, if I take this one to the left hand side it will become 0. So therefore we could get only 0 equals to 2 plus 4 plus 6, that is equals to 12 into 10 raised to minus 6 plus Q4. So therefore the value of Q4 is equals to minus 12 into 10 raised to minus 6 coulomb. That is, the Q4 must be minus 12 microcoulomb. This much amount of charge must be placed at the fourth corner. At the fourth corner, that is at D, we need to place minus 12 into 10 raised to minus 6. That is minus 12 microcoulomb should be placed at the corner D to make the total electric potential at the center of the square 0. Okay. Let's move to the next question. That is, a wire having length 2 meter, diameter 1 millimeter and resistivity 1.963 into 10 raised to minus 8 ohm meter is connected in series with a battery of EMF 3 volt and internal resistance 1 ohm. Calculate the resistance of the wire and current in the circuit. Here we can see the length of the wire, we have here 2 meter and diameter of the wire is equals to 1 millimeter, that can be written as 1 millimeter, that can be written as 10 raised to minus 3 meter, and resistivity is equals to 1.963 into 10 raised to minus 8 ohm meter, which are connected in series with a battery of EMF. So we have an EMF here, EMF equals to 3 volt and the internal resistance we have 1 ohm. So we need to find out resistance of the wire and the current in the circuit. We have a relation between resistivity and resistance, that is resistance is equals to resistivity length divided by area of cross section. So we know that the area of cross section of the wire can be written as pi r square, but we don't have here radius, we have here diameter. So therefore this must be expressed in terms of diameter now. So let me write r is equals to, so here r is equals to rho L divided by pi r. So this, instead of writing r is equals to diameter divided by 2. So d by 2. Let me write diameter divided by 2. So whole square. This can be written as now r is equals to, that is rho L divided by pi d square divided by 4. So now we will get r equals to 4 rho L divided by pi d square. Now you could substitute the values, that is 4 into rho. Here we have resistivity, that is 1.963 into 10 raised to minus 8 into length of the wire is 2 meter divided by pi 3.142 into d square, that is diameter equals to 10 raised to minus 2, sorry minus 3, and if I square it then it will become 10 to the power minus 6. Okay. Now on calculating we will get 4.998 into 10 raised to minus 2 ohm. So this can be written as, that is R is equals to, resistance is equals to, this is very nearly equals to 5, so therefore we could express as 5 into 10 raised to minus 2 ohm. This is the resistance. Now we need to find out the current in the circuit. So we know that the current in the circuit is equals to EMF of the battery divided by external resistance plus internal resistance of the cell or battery. So now here we have EMF equals to, so EMF 3 volt we have, and then here resistance, just now we got the resistance is equals to 5 into 10 to the power of minus 2 plus the internal resistance equals to 1. So therefore 3 divided by, so 5 into 10 raised to minus 2, this net 0.05 plus 1. So this can be written as 3 divided by 1.05. So 3 divided by 1.05 gives us I is equals to 2.85 ampere. Okay. So here we will get our resistance is equals to 5 into 10 to the power minus 2 ohm, and the current in the circuit equals to 2.85 ampere. Okay. Let us move to the next question. That is, an inductor and a bulb are connected in series to an AC source of 220 volt 50 hertz. An inductor and a bulb are connected in series to an AC source 220 volt 50 hertz. A current of 11 ampere flows in the circuit and phase angle between the voltage and the current is pi by 4 radians. Calculate the impedance and the inductance of the circuit. Here an inductor and a bulb, that bulb offers a resistance. So it is having a certain resistance. So therefore we can consider this one as a resistor. An inductor and resistor connected in series of to an AC source, that is V equals to, let me consider it is a AC source, V RMS we have, that is 220 volt, and frequency 50 hertz. A current of 11 ampere, that is IRMS, is equals to 11 ampere flows in the circuit and phase angle between the voltage and the current, that is psi equals to pi by 4 radian. That can be written in terms of degree, that is 45 degree. Calculate the impedance and inductance of the circuit. So impedance, so Z is equals to, that we know that Z is the impedance, this is the opposition offered by the LR circuit, so this LCR circuit or LR circuit, that can be written as V RMS divided by IRMS. That is V RMS is equals to 220 volt, and here we have IRMS, that is equals to 11 ampere. So once you will finally get 20 ohm, that is Z is equals to 20, impedance is 20 ohm. Next we need to find out the inductance of the circuit. So that is L we need to find out. So we have a formula for Z, that is impedance is equals to R square plus XL square, because it is only the RL circuit, that is resistance and inductor circuit. So we could write Z equals to square root of R square plus XL square. So therefore we could write now Z square equals to R square plus XL square, that is XL square is equals to Z square minus R square. So to find out XL we need resistance as well as Z. So already we found Z value, that is 20 ohm, but we need to calculate now R. So as we know that cos psi equals to R by Z. So from the phasor diagram you can have this formula, that is cos psi equals to R by Z. So here R is equals to Z cos psi. So here we have Z equals to 20 ohm and cos psi, cos 45 degree, that we know that cos 45 degree is 1 by root 2. So 20 divided by 1 by root 2, that is R is equals to 20 divided by root 2 value is 1.414. So 20 divided by 1.414 gives us R equals to 14.14 ohm, 14.14 ohm. This is the value of resistance. So here we can substitute now, that is XL square is equals to Z square, that is 20 square minus 14.14 whole square. So on simplifying this, we get XL square is equals to 400 minus 14.14 square is nearly equals to 200. So therefore XL square is equals to 200. So now we can have XL, that is XL is equals to root 200. That is root 200 is equals to 14.14. That is XL. So what we need to find out? We need to find out L. So already we know that XL is equals to, this is XL is the inductive reactance that we got now as 14.14 ohm. Now we know that XL, it is the inductive reactance that is given by 2 pi FL. So now 14.14 ohm. So L is equals to 14.14 divided by 2 pi F. Isn't it? Now on substituting the values, that is 2 into pi value is 3.142 into F. Here we have F is equals to 50 hertz, that is 50. So on simplifying, we get 0.0454 Henry. This is the inductance. So here we have impedance is equals to 20 ohm and inductance is equals to 0.054 Henry. Okay. Let me move to the next question. That is, in Young's double slit experiment, while using a source of light of wavelength 4500 angstrom, the fringe width is 5 millimeter. If the distance between the screen and the plane of the slit is reduced to half, what should be the wavelength of the light to get fringe width 4 millimeter? Here we have a source of light of wavelength 4500. Let me take lambda equals to 4500 angstrom, that is 10 to the power minus 10 meter, and the fringe width is beta. Let me take beta equals to 5 mm, that is 10 to the power minus 3 meter. If the distance between the screen and the plane of the slit is reduced to half, that means initially the fringe width, let me consider the initial fringe width, initial distance between the screen and the plane. Initial distance between the screen and the plane is d. And whenever the distance between the screen and the plane of the slit is reduced to half, that is d2 equals to d by 2, what should be the wavelength of the light to get the fringe width of? That means what should be the wavelength? Let me consider this one as second wavelength and the first one is B1 and this is beta 1. What should be the wavelength of light to get the fringe width of 4 millimeter? That is beta 2 equals to 4 millimeter. So we need to find out the wavelength of the light to get the fringe width of 4 millimeter when the distance between the screen and the plane of the slit is reduced to half. As we all know that an expression for the fringe width is given by beta equals to lambda d divided by d. So let me apply for these two situations, that is beta 1 is equals to lambda 1 d1 divided by small d, and beta 2 is equals to lambda 2 d2 divided by d. So I'm dividing beta 2 by beta 1, that is beta 2 divided by beta 1 is equals to, we will get lambda 2 d2 divided by divided by lambda 1 d1, because this d and d get cancels. Now this d2 is nothing but lambda 2, d2 is nothing but d by 2, and lambda 1, d1 is nothing but d. So d get cancels, we will get beta 2 divided by beta 1 is equals to lambda 2 divided by 2 lambda 1. So we need to get lambda 2 here. So make this lambda 2 as a subject formula. So we will get lambda 2 is equals to, that is beta 2, this 2 beta 2 lambda 1 divided by beta 1. On substituting the values, let me substitute, that is 2 beta 2 equals to here 4 times 10 raised to minus 3 meter into lambda 1 is equals to 4500, that is 4500 into 10 raised to minus 10 divided by beta 1. So beta 1 is equals to 5 into 10 raised to minus 3, 5 raised to 10 to the power of minus 3. So on simplifying this, we will get lambda 2 is equals to this 10 to the power of minus 3, 10 to the power of minus 3 get cancels, and here 5 1 ja, 5 9 ja, 4 2 ja, 8 8 9 ja, 72, that is 7200 into 10 raised to minus 10 meter, that is lambda 2 is equals to 7200 angstrom. So this is the wavelength of the light used to get fringe width of 4 millimeter when the distance between the screen and the plane of the slit is reduced off. Okay, so let me move to the next question, that is the activity of a radioactive substance is 4700 per minute. The activity, that is initial activity we have here, the activity of the radioactive substance A naught is equals to 4700 per minute. 5 minutes later, that is after time t, activity is, that is 5 minutes, that is after 5 minutes, the activity is 2700 per minute, that is activity of the radioactive substance is 2700 per minute. Now our aim is to find out decay constant and half-life of the radioactive substance. As we all know that A is equals to radioactive substance, A equals to A naught e to the power of minus lambda t. So let us see the first one. Now we know that E can be written as E to the power of minus lambda t can be written as A divided by A naught. Here lambda is the decay constant that we can get now. So as we know that e to the power of lambda t will become now A naught by A. Now on substituting the values, we get e to the power of lambda t is equals to A naught. The A naught value is 4700 per minute and A equals to 2700 per minute. And this two zeros get cancels. 47 divided by 27, that is e to the power of lambda t equals to 1.7407. So now taking log on both the sides. So if I take log on the both sides, then we'll get lambda t is equals to log E 1.7404. You know that the log E should be written in log 10 form, so it will become 2.303 log 10 1.7407. So here we know that is lambda t. So here t is equals to how much? 5 it is. So now 5 lambda can be written as 2.303 and log 10 1.7407. Here 1, we have here 1. So here characteristic will become 0, and then for 17 we have to see the common log table, that is 74, that is 17. We can see 17 row, we have to see 17 row, fourth column in this we can say 2405, and then here we have for 1 2, so we will get 2407. The value of this one is 2407, that is 2407. This is equals to, now lambda is equals to 2.303 into 0.2407 divided by 5. On simplifying, we get lambda, that is lambda equals to 0.1108 per minute. This is the value of decay constant. Okay, now let me go to the second part, that is half-life of the radioactive substance. We know the relationship between half-life and decay constants, that is half-life period of the radioactive substance is equals to 0.693 divided by decay constants. So we know that the lambda value equals to 0.6, here 0.1108. On simplifying this, we get T off equals to 6.25 minute. This is the half-life period of the radioactive substance and it is a decay constant. Okay. So these are the questions which appeared in the July 2016 paper. Okay. Thank you for watching.